let me get started. So this is a short talk. It's going to be a very focused talk in that regard, that I have picked a particular problem that I have run relatively recently. And I found it interesting because it is not only a distance geometry question, but it is connected to some other problems of convex and discrete geometry. So as you see in my title, there are two things that are entering here. Minkowski space is a terminology that's often used for finite dimensional norm spaces. I really just take a real vector space and assume that there is a norm associated with that, and that we call a Minkowski space. And then I will talk about point configurations. Excuse me. So let's see. This starts with an old paper of Clinton Patty, which was published in 1971. And as you see in the title here, Patty was dealing with a very simple geometric question. He looked at equilateral point sets in a given finite dimensional norm space. An equilateral point set is perhaps the simplest possible, with pairwise distances equal to a given positive value. And he was interested in the question, what's the maximum cardinality of such an equilateral point set? Well, in the Euclidean setting, this is obvious. It's well known that in d-dimensional Euclidean space, the maximum cardinality of an equilateral set is just d plus 1. However, if we move to other norm spaces, then this question becomes more interesting. So that's the topic in his paper. Let's see what he has managed to prove. So his first theorem you will see down here in this slide. And in order to understand what he claims here, we just need to review the notion of antipodal point sets. So a finite point set he calls an antipodal point set if it has the property that no matter how we choose 2 points, pick 2 points from the point set, then these 2 points lie on parallel supporting hyperplanes, distinct parallel supporting hyperplanes of the point set. So one point lies on one supporting hyperplane, and the other point must lie on the other distinct parallel supporting hyperplane. If that happens for any 2 points in the point set, then he calls the point set antipodal. And then his theorem here says that if we take an equilateral point set in n-dimensional Minkowski space, then it must be antipodal. He can do a little bit more, but it is just fine to understand that his conclusion is that every equilateral point set is in fact an antipodal one. This is his first theorem. And then in the same paper, he comes up with this second theorem, which says that if we now take an antipodal point set in Rn, in the real n-dimensional vector space, then there is a norm on Rn such that this antipodal point set becomes an equilateral set. So one could simply say that an antipodal point set in Rn is in fact an equilateral point set if we choose a proper norm. And if we have an equilateral point set in a norm, then it must be antipodal. So a point set is antipodal if and only if it is an equilateral point set with a properly chosen norm. On the other hand, he actually raised an interesting problem here in this very short paper. First, I just want to recall his third theorem from this paper, which states that if we take a maximal equilateral set in n-dimensional Minkowski space, In other words, an equilateral set which we cannot enlarge, preserving the equilateral property, then the cardinality of such a set is at most 2 to the n, and it is at least 4. From his point of view, the lower bound was actually more interesting, and that's the new component of his paper, namely the upper bound that he has here in this theorem relies on a paper of 2 other authors, and it has been known by the time he has published this paper. So as we now know, if we take a maximal equilateral point set, then it has to be antipodal. And so one can recall this rather classical and well-known paper of Danzer and Grünbaum, in which they show that if we are in Rn and we take an antipodal point set, then its cardinality at most 2 to the n. And this is a sharp result, because if you take a cube in n-dimensional space, it has 2 to the n vertices. And it is not hard to see that no matter how we choose any 2 vertices of a cube, it lies on 2 distinct parallel supporting hyperplanes. In fact, one can take a affine cube for this purpose. So this gives the upper bound 2 to the n here. And the lower bound, he managed to prove 4. If n is larger than this left-hand side is 4 here, led him to his famous conjecture that has been around for quite some time, since that paper, in which he claims that if we take an n-dimensional Minkowski space, and then we can always find at least n+1 points that form an equilateral set. And interestingly enough, this elementary question seems like a deep question. In dimension 3, it has been proved in 2 as well by him. And then Makayev proved it for 4-dimensional spaces. And we know a couple of other results, which I'm not citing here, for other norms, special norms. So there is this nice survey article of Swanepoel, which gives quite an overview on the status of this odd conjecture of Petty. Now, before I get to the new part, I want to recall 2 additional problems which are going to be related to what I'm going to talk about. So, okay, we have reviewed Petty's article. I will return to that at some point later. But now let me recall another old conjecture here, which is due to Borshook, or some call it Borshook partition problem, which is about partitioning a set of diameter 1 in, say, d-dimensional Minkowski space into sets of smaller diameters. So this number, Borshook number, that I have introduced here in this definition for a given d-dimensional Minkowski space is the smallest integer m, such that any set of diameter 1 can be partitioned into m sets of smaller diameter. Borshook raised the problem whether in d-dimensional Euclidean space this value is equal to d+1, whether any set of diameter 1 can be partitioned into d+1 sets of smaller diameters. Now, I'm not going to review it in details here. We know that this has been proved for dimension 2 and in dimension 2 and 3. And it was a surprising result of Kahn and Karoly when they found a counterexample to this conjecture for high dimensions. I'm just highlighting here from the abstract the part which helps to understand that in large dimensions, this number has to be exponential, 1.2 raised to square root of d, so it's much larger than d plus 1. On the other hand, we know upper bounds for the Borshook number of d-dimensional Euclidean spaces. Namely, Lassak proved in 82 that this any set of diameter 1 can be partitioned in this space, can be partitioned into smaller diameter sets. Not too many sets we can create here, namely at most 2 to the d minus 2 raised to d minus 1 plus 1. So we can always partition any set of diameter 1 into that many sets of smaller diameter. And this has been improved for larger dimensions by Schramm. His upper bound you see here, still exponential in d, but better than Lassak's upper bound if d is at least actually 18. And that's fine for this talk today here. This knowledge is sufficient for the rest of my talk. But if you want to take a closer look of the status of Borshook problem, then here's Rygorodsky survey article, for example, that gives a nice overview of that. The other conjecture that I want to recall here is due to Hadwiger. It's by nature similar to Borshook's covering problem. In this case, what we want, say we have a finite point set, we take the convex hull of that set, and we want to cover that convex hull by smaller homothetic copies using not too many smaller homothetic copies. So in this way, we can introduce the Hadwiger number of Rd. And in this way, this is the smallest positive integer L, such that no matter we choose finitely many points in the convex hull, we can always cover that convex hull by L smaller homothetic copies. Smaller here means that the coefficient, homothetic coefficient, is between 0 and 1. And the conjecture that Hadwiger made is that this can always be done by 2 to the d smaller homothetic copies. We know this conjecture in dimension 2, but this conjecture is open for dimension 3 and higher. A classical odd upper bound is due to Rogers. He proved this upper bound for the Hadwiger number of the d-dimensional space. And as you see, the order of magnitude is unfortunately much higher than the desired conjectured order. As in the case of the Borshook conjecture, there are further upper bounds. Lassak proved an upper bound which improves Rogers' upper bound in some small dimensions. And just very recently, these 4 people here improved Rogers' upper bound for very large d. And this is their upper bound. C1 and C2 here are absolute constants. They are not dependent on d. So this improves Rogers' upper bound when d is very large. On the other hand, Lassak upper bound improves Rogers' upper bound for small values of d, and then Rogers is still the best in between. Again, there is a survey article here on this problem. It has been heavily investigated, just as the Borshook conjecture. I stop here. These 2 problems are going to play a role for my remaining part of talk. Namely, the new topic is an extension of Petty's results. So actually, what I want to really get to is an extension of Petty's article to point configurations, which I call k-diametral point configurations. And for this question here, I will use our knowledge on the Borshook problem and Hadwiger problem, as you will see at some point later. Nevertheless, let me get to the definition that what I mean on a k-diameter point configuration. So the first paragraph here just refreshes our knowledge that d-dimensional Minkowski space I imagine as RD equipped with a norm. And geometrically, that means that I choose an origin symmetric convex body in RD. And I think of that origin symmetric convex body as the unit ball of my norm. And I denote this unit ball by K0 here. And then we can talk about k-diametral point configurations in a d-dimensional Minkowski space. So that means we choose a labeled point set. Here I choose capital X for this purpose with points x1, x2, xn. So this is a labeled point set, and I say this is a point configuration of n points. But actually here it is allowed to choose the same point, as many times as you like. So a point configuration here is a point set with points having some multiplicities. And the sum of the multiplicities is n. So whenever we talk about a point configuration of n points, we should keep in mind that the points need not to be distinct. And they lie in this case, in a d-dimensional Minkowski space. And we call such a point configuration a k-diametral point configuration if it has the property that among any k tuples that we choose from our n points, always there are two whose distance is equal to the diameter of the given point configuration. So no matter if we choose a k-tuple, we should be able to find two points among them whose distance is equal to the diameter of the given point configuration. If that holds, then I call that point configuration a k-diametral point configuration. Of course, a two-diametral point configuration is simply an equilateral point configuration. And Patty has managed to maximize the cardinality of a two-diametral point configuration in d-dimensional Minkowski space, as we discussed a few minutes ago. In fact, also he was able to give a bit more insight to it, realizing that that is equivalent to saying that the point configuration is antipodal. After this, let's see what is the connection to this problem, to my problem, on maximizing the cardinality of k-diametral point configurations in given d-dimensional Minkowski space. So this maximum I label by f sub k of m d sub k0. So this is the maximum cardinality of a k-diametral point configuration in the d-dimensional Minkowski space. And as you see here, this we can upper bound by the Borshook number of the d-dimensional Minkowski space, and we can lower bound it by the maximum cardinality of the equilateral point configuration, where I really put 1 over k minus 1 in front of f sub k. So this squeezes my maximum cardinality number between these two numbers, And in fact, well, the Borshook number can be upper bounded by the Hadwiger number of RD. That's how I got this upper bound, which depends on the dimension only, doesn't really depend on the actual norm that we are using for the d-dimensional Minkowski space. On the other hand, in a two-dimensional case, we actually understand this problem pretty well. It turns out that the maximum cardinality of k-diametral point configurations is just simply equal to k-1 times the maximum cardinality of equilateral point configurations in that given two-dimensional Minkowski space. However, in higher dimensions, the question is quite challenging and remains open. Even in the case when the norm is Euclidean, I know only in dimension 2 and 3 the exact values of the maximum cardinalities of k-diametral point configurations. That's given by this formula. And starting from dimension 4, I have only these estimates, what you see here. And you know, this shows that there is a gap here, in particular, because if the Borshook number of the d-dimensional Euclidean space is really larger than d plus 1, and now we know it can become larger due to Karoly-Kahn's result. So in that case, there is a gap between the lower and upper bound, which you see here in this statement. So let me just point out that the two-dimensional case is really well understood because in the two-dimensional case, the following statement holds that the maximum cardinality of the equilateral set in a two-dimensional Minkowski space is equal to the Borshook number of the two-dimensional Minkowski space. This has been done in these different papers. Boltiansky and Zsolt independently from Grünbaum observed that the Borshook number of a two-dimensional Minkowski plane is 3 if the norm is different from the L infinity norm, and it is 4 if we look at the L infinity norm there. And Patty, in the paper that we briefly discussed, has shown that the maximum cardinality of the equilateral point set in two-dimensional Minkowski plane is 3 if the norm is different from the L infinity norm. It is 4 if it is the L infinity norm. So after this, let me show you how I go about extend or finding the analog of Patty's theorem for k-diametral point configurations. The missing part is this here. We need to introduce the notion of k-antipodal point configuration. And this is done in a way very similar to the definition of k-diametral point configuration. So we take our favorite I mean, in this case, I'm not going to talk about any norm, so I just take RD. And we know how to introduce antipodal point set in RD. We discussed that briefly. Here we extend it in this way, and we introduce k-antipodal point configurations in RD. As follows, we say that a point configuration of endpoints is k-antipodal if among any k-tuple we are always able to find 2 points that lie on distinct parallel supporting hyperplanes of the given point configuration. So that means that, well, you know, we can say that, well, a 2 antipodal point configuration is simply just an antipodal point configuration. So if f sub k of d stands for the largest cardinality of a k antipodal, I mean, largest n for which there exists a k antipodal point configuration of n points, then we know the value of capital F sub 2 of d, namely that's just 2 to the d. This is the maximum cardinality of an equilateral of an antipodal point set in RD, proved by Dancer and Grünbaum. And then the question remains about the other values of f, capital F sub k of d. Just very briefly, I want to emphasize here that Dancer and Grünbaum did a little bit more because they could use a result of Grömer. And that's the result I quoted here, which states that if you have a convex body and you dissect it into homothetic convex bodies, then that convex body must be actually an affine cube. This is the result of Grömer that actually implies that equality here happens only in a very special case, namely if capital X is an antipodal point configuration of 2D points in RD, then those 2D points must be the vertex set of an affine cube. Okay, so after this, here's the extension of Petty's result, which says the following. The point configuration capital X is a k-antipodal point configuration in RD, even only if there exists a norm. In other words, there exists an origin symmetric convex body such that X is a k-diametral point configuration in the d-dimensional Minkowski space induced by K0. Moreover, we actually know the maximum the largest number n of with the property that there exists a k-antipodal configuration of endpoints in RD. Namely, the largest number is k minus 1 times 2 to the d. Moreover, we, just as in the case of Dancer-Grünbaum theorem, we can say a little bit more, namely, if we have a d-dimensional Minkowski space with the property that the largest number of largest n for which there exists a point configuration, which is a k-diametral point configuration, is equal to k minus 1 times 2 to the d, then the norm must be the L infinity norm, and the k-diametral point configuration of that many points must be identical to the vertex set of a homothetic copy of a D cube, with each vertex having multiplicity k minus 1. So in short, I could say that this is quite a natural extension of Petty's theorem to k-diametral point configurations. And it gives some geometric understanding of k-diametral point configurations in terms of this notion being k-antipodal. If we want to go do a little bit more, I cannot really do much more, honestly. This is a topic which is likely to be extended further. Right now, I have an aspect of it which is perhaps going that direction, which would you call even more natural. We could namely talk about k-antipodal point set as well, k-diametral point sets. Here, I replace the notion of point configuration by point set. So the difference is that now when we talk about the point set, we know that the points are pairwise distinct. And so we can talk about a k-diametral point set, which simply means that among any k points, there must be two lying at distance equal to the diameter of the point set. And we can talk about k-antipodal point sets as well, which means that among any k points, there must be two lying in distinct parallel supporting hyperplanes of the point sets. And then we can introduce their maximum cardinalities and label that by small g sub k of m d of k0, so and capital G sub k of d. And well, naturally, the upper bounds that we introduced for point configurations work here for point sets. And that's why I'm putting down this inequality here. So also that means that we have a very similar inequality to the largest cardinality of k-antipodal point set in RD is at most k minus 1 times 2 to the d. But the question here becomes suddenly more interesting from the point of view of geometry, because, well, when we actually look at capital G sub k of d and try to evaluate it for k and d, particle choices k and d, the problem becomes quite challenging. What we know the two-dimensional case. The largest cardinality of a k-antipodal planar point set is 2 times k. And in fact, we can characterize the extremal point sets here, which you can see here. In this part of the theorem, I give a characterization. This includes, of course, the regular 2k gon, but there are other extremal configurations that enter here. And if the dimension is at least 3, then we have only these bounds available. So I know only this, that the largest cardinality of a k-diametral point set in RD is between these two numbers. It would be nice to do more and to say more about these antipodal k-antipodal point sets, about to say more about the maximum cardinality of k-antipodal point sets. I put down here this question: perhaps the largest cardinality of a k-antipodal point set in RD is equal to k times 2 raised to d minus 1. There is a construction which gives this number. That much I know, but whether that is really the highest number, I don't know. The problem becomes equally interesting when we turn to k-diametral point sets in a given d-dimensional Minkowski space. Well, if the norm is the L infinity norm, then we know the largest cardinality of a k-diametral point set, namely that is k times 2 raised to d minus 1. But if we change that norm, then the problem becomes quite challenging. Already in the Euclidean case, I know only this, what you see here in this part of this theorem. The largest cardinality of a k-diametral point set in 3-dimensional Euclidean space lies between these two values. Unfortunately, there is a gap here. And the exact value which is not immediate from here for G sub 3 of E3 is 6. And in fact, the external configurations are quite interesting because they are quite, there is a number of them, which you see listed here.